There is an equation that describes everything you have ever touched, tasted, seen, or heard. Every atom in your body, every photon that has ever hit your eyes, every electron that has ever carried a signal through the wire. That equation is called the Schrödinger equation, and its solution, the thing it spits out, is called the wave function. The wave function is the most complete description of reality that physics has ever produced. It tells you everything knowable about a quantum system. Its energy, its momentum, its position, its spin, all of it encoded in one mathematical object, written as the Greek letter psi. So what is it? That question has a short answer and a long answer. The short answer is a wave function is a probability amplitude, a mathematical object that tells you the probability of finding a particle in any given state when you measure it. The long answer is what the video is about, and the long answer is much more stranger. So before we can understand the quantum wave function, we need to understand what a wave actually is, because the word gets used loosely and it matters here. A wave is a disturbance that propagates through space and time. When you drop a stone in water, a circular ripple moves outward. The water molecules themselves are not traveling across the pond. What travels is the pattern, the shape of the disturbance. That shape moves. Every wave has three properties that define it completely: amplitude, how large the disturbance is; wavelength, the distance between the two peaks; and frequency, how many peaks pass a point per second. Waves also do something particles cannot do. They interfere. When two water waves meet, they add together. Where both are cresting, they create a bigger crest. When one is cresting and the other is trowing, they cancel out. This is called constructive and destructive interference, and is one of the most important phenomena in all of physics. Now here's where things get strange. In the early 20th century, physicists discovered that particles, electrons, protons, photons, also interfere. An electron is fired at two slits creates an interference pattern on the screen behind, just like water waves do, but an electron is a particle. It has a definite mass. It hits the screen at one specific point. How can something be a particle and also interfere like a wave? The answer is the wave function. The wave function is not the electron. The wave function describes the electron, and the wave function behaves like a wave, even when the electron ultimately behaves like a particle. The wave function is a complex valued function of position and time. We write it as psi of x and t. At every point in space and every moment in time, it has a value. That value is a complex number, a number with both a real part and an imaginary part. This is the simplest wave function, a plane wave. A is the amplitude, k is the wave number related to momentum, and omega is the angular frequency related to energy, and e to the ikx minus omega t is a rotating complex number that sweeps through the complex plane as x and t change. Think of it this way. Every point in space, the wave function has a magnitude and a phase. The magnitude tells you how large the probability amplitude is. The phase tells you the angle of the complex number in the complex plane. As time passes and you move through space, this phase rotates. That rotation is what makes the wave function a wave. Now here's the key connection between the wave function and physical reality: the Born rule, named after Max Born, who proposed it in 1926. The Born rule says the probability of finding a particle at position x when you measure it equals the squared magnitude of the wave function at that position. The absolute value squared of a complex number is always a real non-negative number, so this probability is always real and always non-negative. If you integrate it all over space, add up the probabilities everywhere, you get 1. The particle has to be somewhere. This is the normalization condition. This single equation, the Born rule, is the bridge between the abstract mathematics of the wave function and the concrete probabilities we actually measure in experiments. The wave function itself is not directly measurable, but its squared magnitude is, because that gives you probabilities, and probabilities are things you can check by running an experiment many, many times and counting outcomes. Here is where the strangeness really sets in. Before measurement, the wave function can be a superposition, the sum of multiple different states at the same time. A particle does not have a definite position. It has a wave function spread across space, encoding the probability of being found at each location. It's not secretly at one location that we just don't know. The wave function is the complete description. There is no hidden position. That particle generally does not have one. This is a radically different from classical probability. If I flip a coin and cover it, the coin is either heads or tails, I just don't know which. Classical uncertainty is about ignorance. Quantum superposition is not. Before measurement, an electron is in superposition, is genuinely in multiple states simultaneously. The wave function encodes all of them at once. We can write superposition state as this, where psi1, psi2, and psi3 are different possible states, different positions or different energies or different spins, and c1, c2, c3 are complex coefficients. The probability of finding the particle at state n is absolute value of c and n squared, and all these probabilities must sum to 1. The coefficients carry the phase information, and the relative phases between the different terms in the superposition determine how the wave function evolves and whether different terms interfere constructively or destructively. This is why phase matters so much in quantum mechanics and quantum computing. The phase is not directly observable, you cannot measure it directly, but it controls whether the quantum states add up or cancel out, and adding up or canceling out is how quantum algorithms work. Now for the most philosophically loaded part of the wave function. When you measure a quantum particle, when you force it to interact with a measuring device in a way that records a definite outcome, the wave function collapses. So before measurement, the particle is in a superposition of many possible states, described by a spread out wave function. After measurements, you get one specific outcome, the position of the particle or its spin or its energy, one definite value. And after that measurement, the wave function is no longer spread out. It has collapsed to a narrow peak at the measured value. Mathematically, if you measure position and find the particle at x0, the wave function immediately after measurement becomes a spike at x0. In the idealized version, a Dirac delta function, all the probability is now concentrated at that one point. This collapse is instantaneous. It doesn't propagate at the speed of light. It happens everywhere at once the moment the measurement occurs. This troubled Einstein enormously. He called it spooky action at distance when applied to entangled particles. If two entangled particles are separated by a light year and you measure one, the wave function of the other collapses instantly. Now here's the honest thing to say, nobody fully agrees on what the wave function collapse actually is. The Copenhagen interpretation, which is the oldest and most widely taught, says that the wave function is a calculational tool. It gives you probabilities. When you measure, you get an outcome and you update the wave function. Don't ask what it means physically, just shut up and calculate. The many worlds interpretation says the wave function never collapses. Instead, every measurement causes the universe to branch. Every possible outcome happens in a different branch of a universe wave function. You end up in one branch, and other versions of you end up in the others. The pilot wave interpretation says the particle always has a definite position, guided by the wave function as a real physical field. The wave is real, the particle surfs it. Physicists have been arguing about this since 1926. All three interpretations make the same experimental predictions. The math is the same, the philosophy is where they differ, and it's not resolved. It's a gap that will close next year. I mean, it's not, actually, unfortunately. But it is one of the deepest, most open questions in physics. So the wave function does not stay still. It evolves in time, and the equation that governs it, its evolution, if you will, is a Schrödinger equation. We covered the Hamiltonian in a previous video. The Hamiltonian is a total energy operator. The Schrödinger equation says that the rate of change of the wave function in time is determined by the Hamiltonian acting on it. Energy drives time evolution. For a free particle with no forces acting on it, the Hamiltonian is just kinetic energy operator. Plugging this in, the Schrödinger equation becomes a wave function, the same mathematical structure as a wave on a string or a sound wave or a light wave. The quantum wave function propagates, spreads, reflects, and interferes according to the same basic mathematics. For a particle in a potential, which is an electron or proton, a particle in a box, qubit in a magnetic field, the potential energy term V of x is added to the Hamiltonian. Different potentials give different wave functions. Solve the Schrödinger equation for the hydrogen atom column potential, and you get the atomic orbitals, the SPDF, shapes that determine all of chemistry. Those orbital shapes are the square magnitudes of the hydrogen atom wave functions. The wave function is not just a theoretical object, it's directly connected to the shapes you see in chemistry textbooks. Those cloud diagrams of atomic orbitals are literally pictures of psi squared. The wave function is the foundation of everything in quantum computing. A qubit state is a wave function. When we write ket psi equals alpha ket 0 plus beta ket 1, that is a wave function in the two-dimensional Hilbert space of a spin-half particle. Alpha and beta are complex coefficients of the superposition. Their magnitude squared gives the measurement probabilities. The relative phase determines how the qubit state evolves under the quantum gates. When a quantum gate acts on a qubit, it transforms the wave function. An X gate flips alpha and beta. A Hadamard gate creates an equal superposition. A phase gate rotates the phase of one component. Every gate is a rotation in the space of wave functions, a unitary transformation that preserves the normalization condition. When you run a quantum algorithm, you are engineering the wave function of many qubits to evolve in a specific way. You want the amplitudes of the wrong answers to interfere destructively, to cancel out, and the amplitudes of the right answer to interfere constructively, to add up. Grover's algorithm does this for search. Shor's algorithm does this for factoring. QAOA does this for optimization. Every quantum algorithm is, at its core, a carefully choreographed evolution of a wave function. The wave function is not a curiosity, it is the entire computational substrate of quantum computing. And decoherence, which we covered in a previous video, is exactly what happens when the wave function of your qubits leaks into the environment and becomes entangled with everything around it. The superposition does not vanish, it spreads out until recovering it is impossible. That is why decoherence destroys quantum computation, because quantum computation is a wave function manipulation, and decoherence destroys the wave function's coherence. Here's the honest way to answer the question that we started with. Mathematically, the wave function is a complex valued function that encodes all knowable information about a quantum system. Its squared magnitude gives you probabilities, its phase drives interference. It evolves according to Schrodinger's equation. When measured, it collapses to a definite state. Physically, we do not know. We do not know if the wave function is a real physical object that exists in the world or a mathematical tool that lives only in our equations. We do not know what happens during collapse or if collapse happens at all. We do not know whether other branches of the wave function are real. These are not engineering problems waiting for a bigger computer. They are foundational questions about the nature of reality that the physics community has not agreed on in a century of trying. What we do know is that the wave function works. It is the most precisely tested theory in the history of science. Quantum electrodynamics, the quantum field theory of electromagnetism built on wave functions, predicts the magnetic moment of the electron to 11 decimal places. 11. No other theory in any field of science comes close to that precision. Whatever the wave function is, it is describing something real, something that underlies every atom, every particle, every quantum computer being built right now. We just do not know what that something is. And the fact that our most successful theory of reality is built on an object whose physical meaning is still being debated is one of the most extraordinary things about physics. The wave function, a complex valued function of space and time, the complete description of a quantum system, the foundation of quantum computing, one of the deepest unsolved mystery in all of science. Thank you for watching, and keep questioning quantum world. I'll catch you the next time.